Number 43, let x and y be independent with the following density functions: f of x equal to 1 between 0 and 1 and 0 elsewhere, and f of y equal to 2y, where y is between 0 and 1 and 0 elsewhere. What is the probability that y is less than x? Problem 43. Here we're given that x and y are independent. So the product of their joint, or the product of their marginal distributions, is the joint distribution. So here we're trying to find that y is less than x, which is this region. X and y go from 0 to 1. So we integrate the joint distribution over this region. And we're going to go from, y is going to go from 0 to x, and x is going to go from 0 to 1. So we're going to integrate with respect to y first, so we get y squared, plug in the values, then we integrate with respect to x, and we get this, plug in the range, we get 1/3. Number 44, suppose x1 through xn is a random sample from the uniform distribution on 0 to 1, and let z be the sample range. What is the probability that z is less than or equal to 1/2? Problem 44, it asks us to find the distribution of the range. Now the range is the largest value in the sample minus the smallest value in the sample. So we set up some order statistics. Y1 is the minimum of our data, and xn is the maximum of our data. Now each xi is uniform 0 to 1, which is what this says. Our density is 1, and the CDF, or the cumulative distribution function of x, is just x when we're at a uniform 0 to 1. Now on these tests, all 8 tests, it sort of assumes that you know how to create a joint density for order statistics. So I'm not going to go over this. And deriving this, I think each time on a test would not be worthy. So creating order statistic distributions is something worth investigating if you're not comfortable with it. But plugging in, finding the joint density of y1 and yn when we're in a uniform ends up being this distribution here. Now, we want to go from R2 space, y1 to yn. We need to map it to R2 space, so we're going to create 2 variables. R is a sample range, which is of interest, and S is sort of a dummy variable. So we find the joint distribution of R and S, and then we integrate out S that leaves just R. So here, finding the range, or the range of what we're going to integrate out over X can be tricky sometimes. So setting up a graphical illustration of this often helps. So if we have y1 and yn, and then you find the range of y1 and yn, remember that y has to be strictly less than yn. So that restricts us to the top side of this diagonal line. And then since y1 and yn rank go from 0 to 1, we're in this triangle. And then to find the range for R and S, what you do is you take each boundary and then you map it, you find where it maps to in this other region. And I've done that with ticks. Double tick goes to this boundary, this top line goes to the diagonal. And so this gives us a picture of what we're going to integrate out. So we're going to integrate out S going from 1 minus R to 0. So the distribution of R is the joint distribution of R and S with S integrated out. But this joint density is you use the F1 and Fy1 and N1 density with these values plugged in for y1 and yn. So when you plug these values in for here, and R plus S in for yn, then you get this. So we just plugged in the R plus S and minus S. Well, these S's cancel, and then everything else is a constant, so it can be taken outside the integral sign. And then integrating with respect to S, we get this and then R goes from 0 to 1. So this is the density of the sample range. Well, then we need to find the probability that R is less than a half. So we integrate our density, which we just found, from 0 to a half. And then we get this, and we got to plug in our range here. Now when it's 0, all that cancels, so just the 1/2 is relevant. And we plug it in, simplify it, and we get m plus 1 times 1/2 to the n. Problem 45. In order to test the hypothesis that that mu is equal to 60 against the alternative that mu is not equal to 60, a sample size of 101 was taken. A summary of this data is shown below. Which of the following defines an approximate 95% confidence interval for mu? Here, problem 45, we want to find a 95% confidence interval for mu. Well, we're in a t-distribution. Well, since we don't know the sample, the population variance or the standard deviation, we're technically in a t world, where S is the unbiased estimate of the sample standard deviation. So then the formula is given by this. But a t of 100 degrees, my table doesn't go that far with 100 degrees of freedom. So since it's a large sample, we're going to just substitute it with z and go from there. And so this all drops out and we get 50 plus or minus 1.96, which is the z value given for that specific alpha of 0.05. 46. Let x and y be two independent random variables with respective density functions. F of x equal to 3x squared when x is between 0 and 1 and 0 elsewhere, and g of y is equal to 4 times y cubed where y is between 0 and 1 and 0 elsewhere. What is the expected value of x divided by y? 46. One note is that when x and y are independent, then functions of x and y are independent. And that's pretty straightforward to prove. So when they ask for the expected value of x and y, that's the same as x times 1 over y. Well, since y and x are independent, we can break them up. And then we just need to find the expected value of x, which it goes from 0 to 1, and we get 3/4. And the expected value of 1 over y, we plug 1 over y into our density, and it ends up being this. We integrate, we get 4/3. So the expected value of x divided by y is 1. Problem 47. A researcher selected a random sample of 100 observations from a normal distribution to test the hypothesis that mu is equal to 50 against the alternative that mu is greater than 50. If sigma equals 15 and the level of significance is 0.05, what is the power of the test to the nearest 100 when mu is equal to 52? Problem 47, it asks about the, what's the power of the test? So first we have to find the rejection region. So we're given that we have a mean of 50 and a standard deviation of 15. Well, what is C? Well, we have to back calculate it from the standard normal. So we know that an area of 0.05 is a 1.645 cutoff value. And then we use this standard formula to back calculate what C is. And C is 52.4672. Whoop. And then we take that C, which is the rejection region. So we want to find the probability that an X bar is greater than C. So we subtract the mean, which we're under the alternative, which they're saying is 52. We divide by the standard deviation of X bar, which is this. Well, plugging in our C, we get Z is greater than 3 or 0.311. We look that up in a Z table and we get 0.38. Problem 48. Suppose that X and Y are random variables with joint moment generating function as defined for all real T1 and T2. What is the covariance of X and Y? Problem 48, we're given a moment generating function, a multivariate moment generating function. And so one property is that if you take the n1th partial and the n2th partial of T2, plug in to 0, that is the expected value of y raised to the n1 and x raised to the n1 and y raised to the n2. And we're going to need this because the covariance is what it's the expected value of xy minus the expected value of x times the expected value of y. So to find the expected value of xy, we're going to take the partial with respect to t1 and t2 and evaluate it at 0. And then to find the expected value of x, we just take the partial of t1 and then evaluate it at 0. Same for the expected value of y. So here the expected value, not the expected value, the partial of t1 with respect to the moment generating function is this. Evaluated at 0, we get this. And what's nice is this adds to 1, and so 1 to the 9th power kind of drops out. We get 5 over 2. We take the partial with respect to x2. We get this, evaluated at 0. We get that, which reduces to 15 over 4. And here we have to take the partial of t1 and partial of t2. So I just borrow, you can borrow this one up here, which is a partial of t1, and then take the partial of t2, and you get this. Evaluated at 0, t1 equal to t2 equal to 0. And we get this, and it's nice that that equals 1 again. And then you get 135 over 16. So then just plugging it into the formula of the covariance of xy is equal to the expected value of x times y minus the expected value of x times the expected value of y. Plug in the values and you get minus 15 over 16. Problem 49. Suppose that x1 through xn is a random sample from a distribution with density function f of x beta and 0 otherwise. What is the maximum likelihood estimate of beta? Here it's asking us for problem 49. It's asking us to find the maximum likelihood estimate for beta. Well, given a sample of size n. So here we have to find the joint density for f1 through xn. And since they're all independently, identically distributed, it's just a product of their marginal distributions, which ends up being this. So, this is the product of the xi raised to the 6. This is the sum of xi over beta, beta to the 7n, gamma of 7 raised to the n. So maximizing this is not straightforward. So what we do is we take a one-to-one function of it, specifically the log. So if we take the log of f, which we're just going to call L, maximizing the log of f, you get the same value as if you just maximize the regular function. And so if we take the log of this, we have the log of something divided by something. So it's the difference. So it's the log of this minus the log of this But then since it's multiplication, the log of this times the log of that, we can, the log of this product is the sum of the logs in the same way here. So this breaks down into these four distinct points here. And that, when we take the partial of L with respect to beta, this is a constant, so it drops out. And this is beta. When you take the derivative of this with respect to beta, you get this, the sum of xi over beta 2. This one is a constant. There's no beta there. So here, the 7n is to a power, which then can be taken out front. And so we're taking the derivative of 7n times log of beta. Well, that's 1 over beta, and then 7n were constants. We set it equal to 0, and then we solve this for beta, multiply it through beta squared. So that cancels. We just left with sum of xi. One of those cancel, and the other one's up here. We get this. Solving this for beta, we get the sum of xi over 7n, and that's the maximum likelihood estimate. Number 50. Suppose x1 through xn and xn plus 1 is a random sample from a normal distribution with unknown mean mu and unknown variance sigma squared. Let xn bar equal the sum of the xi divided by n, and Sn squared equal that quantity. If xn plus 1 is an additional observation, what is the value of k so that this quantity has a t-distribution? Problem 50, it asks us to find the value of k that makes it a t-distribution. So let's do a very quick review. If we have a standard normal distribution, z, and we have a chi-squared called x with certain degrees of freedom, then if we take z divided by the square root of the chi-squared divided by its degrees of freedom, that's a t-distribution with the same degrees of freedom. Okay? So in our value, we're given, this is the numerator. So this is the sum of normal variables. So it's also going to be normal. So let's find the expected value of it. Expected value of this minus this is just mu minus mu, which is 0. The variance of these two, now they're independent, so there's no covariance, is the variance of the first one plus the variance of the second one. Factor out a sigma squared, we get sigma squared n plus 1 over n. Now, this sum here divided by the true variance is a chi-squared with n minus 1 degrees of freedom. So we set up this equation here. So t is equal to a standard normal. So we take x n bar minus x n plus 1, and then we divide by their standard deviation, and that's a standard normal. Now we divided by a chi-squared distribution divided by its degrees of freedom, which is this. Well, this simplifies to this expression, which this piece here is what they provide, and so this must be the constant. So that's k must equal n minus 1 over n plus 1 raised to the 1/2 power, or the square root of that.